Hello everyone, I'm Yuanlong Xiao, fourth-year PhD student from the University of Pennsylvania. I'm here today to talk about our recent research called Embedded Processor Stream Links. The first author has already graduated, so I will do the presentation for him. Here is what my talk will include today. I will start with the motivation and introduce the approaches we use and present some of our experiments results and draw a short conclusion. So as we know, latency sensitive data flow streams allow a producer and consumer to operate concurrently. The stream interface is highly used in high-level synthesis. However, there is no out-of-box solution to provide the stream connections between the hard cores and the associated FPGA fabrics. So the DMA can launch a large data transfer between the PS and PL. However, it is not power efficient for small data transfer with fixed setup instantiation time. So this is our eStream will target. With our eStream, you can link multiple hardcore processors together. You can also link the hard processors and hardware kernels without DMA instantiation. So this means one kernel can be easily mapped to either PL to PS without changing any source code, but only change maybe a pragma. You can map the same source to different mapping implementation. So here is our basic infrastructure. So the main infrastructure we implement is within this red box. It includes the software drivers and hardware IPs. So when you want to map your user kernels at the C level, if you map it to the PS, you only need to instantiate a stream instance, and this instance or class has read function and write function you can use. And on the bottom, our C++ driver will handle all the memory operations. So each stream at the C level will be mapped to a ring buffer on either DDR memory or on chip memory. And if your kernel is mapped to hardware kernel, our stream IPs will handle all the data access to the. So we implement our infrastructure on Ultra 96 board, and because we think this is a board most people have access to, and here is some experiments data we have. So for the software implementation, we can use on-chip memory or L2 cache as the shared memory to construct the ring buffer. And for the hardware, we have for the bridge between the PS and the PL, we have several XE channels to use. So by implement different combinations, we find the maximum throughput between the PS is around 500 megabytes per second by using L2 cache as the shared memory, and the fastest throughput between the PS and the PL is around 300 megabytes per second by using L2 cache and ACP channels. So this means the ACP channel is the fastest channel we can use. And for the hardware implementation, the key feature is the XC stream IP we created. So we can equip each user kernel with one or independent XC stream IPs, and as we can connect each XC stream IP to independent XC channels, that means we will use more channels between the PS and PL. So this data shows the throughput we get. We get around 100 megabytes per second throughput, and at the cost of 19K LUTs. So we have another alternative to implement this hardware infrastructure. We can use XC crossbar to connect these stream IPs together, and this means we may have less LUTs overhead, and as we use the fastest channel, ACP channel, we can achieve more throughput than before. And the final implementation we have is to use only one stream IP. It has several stream interfaces, but only has one XC channels. So it still uses one ACP channel, but it has less area overhead. And the final implementation we get is equipped with 100 megabytes per second throughput, and at the cost of 7K LUTs. We also find different data transfer size may affect the throughput. So here is the throughput we get, and here is the conclusion. We provide the PS Stream API, and we can support 100 megabytes per second communication bandwidth. So if you are interested in our talk, you can check our open source link below. Thank you.